Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we drift through black holes, what they are, how massive stars make them, how disks and jets glow around them, and what our best ideas say about the mysterious inside. Soft pacing, plain language, and a gentle tone to settle your thoughts for sleep. But before we get into the topic of discussion for tonight, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. A black hole is not a hole and not really black in the everyday sense. It's a region of space where gravity is so strong that nothing, no matter, no light, can escape once it gets too close. That too close boundary is called the event horizon, and it isn't a wall or a surface you could touch. It's a mathematical boundary in space-time, like a point of no return on a gentle, featureless river. Outside the horizon, the universe behaves almost normally. You can orbit a black hole the way planets orbit stars. Cross the horizon, and all possible paths carry you inward, calmly and inevitably to smaller radii. The simplest way to describe a black hole is with just three numbers: its mass, its spin, how fast it rotates, and its charge, which in astrophysics is usually negligible. A non-spinning, uncharged black hole is described by the Schwarzschild solution, a spinning one by the Kerr solution. The scale is set by mass. Compress the Sun into a sphere about 3 kilometers across, and you have a solar mass black hole. Compress 4 million suns into a sphere smaller than Mercury's orbit, and you have something like the supermassive black hole at the center of our galaxy. The black comes from the fact that light emitted inside the horizon cannot reach us, but black holes are often surrounded by matter, gas and dust, that is falling in, rubbing against itself, heating up and radiating. So in practice, many black holes are outlined by glowing neighborhoods, an accretion disk that can shine in X-rays, jets that can lance out for thousands of light years, and hot plasma that whispers in radio waves. The interior is where our ordinary description ends. The equations say that all the matter collapses toward a central singularity, a place where densities rise without bound, and our current theories no longer apply. That doesn't mean a literal pinprick point exists as we picture it. It means the classical theory admits its own incompleteness at that extreme. Viewed from far away, time near a black hole's edge runs slow. Light climbing out loses energy and reddens. Clocks tick gently but differently. None of this is violent at the horizon itself. If you fell past it in a large supermassive hole, you wouldn't feel a bump. Tidal forces there can be mild. You would only notice, if you were very patient, that the outside world's clocks speed up compared to yours, and all paths forward narrow inward with no route back. In that sense, a black hole is a quiet boundary in the rules, not a thrashing monster. Gravity doing what it always does, only more so, and geometry taking on a shape where outward simply ceases to be a direction that leads away. Most black holes begin life as very heavy stars that run out of fuel. A star shines by balancing gravity, which pulls its mass inward, with pressure from nuclear fusion, which pushes outward. When the fuel in the core changes, hydrogen to helium, then to heavier elements, the balance shifts. In a truly massive star, once the core becomes iron-like, fusion can no longer extract energy. Gravity takes the lead. The core collapses in a fraction of a second. The outer layers, briefly supported, lose their footing. Some rush inward and then rebound in a burst we see as a supernova. Depending on the mass and how much material falls back, the leftover core becomes either a neutron star, a city-sized ball of neutrons, or, if it's heavy enough, a black hole. There are variations on this theme. Some stars may directly collapse into black holes with only a weak or failed supernova, dim fireworks hidden in dust. Stars in tight binaries can feed each other. Mass transfer can push one over the threshold. In the early universe, when gas had fewer heavy elements to cool it, some giant clouds may have collapsed straight into black holes of tens of thousands of solar masses, laying seeds for the supermassive holes we see in galactic centers today. Later on, mergers also help. Black holes orbit each other after their parent stars die, lose orbital energy through gravitational waves, and merge into a larger hole. Over cosmic time, a galaxy's central black hole can grow by swallowing gas that drifts inward and by swallowing other black holes when galaxies collide and combine. The details depend on slow processes, how efficiently gas sheds angular momentum to fall inward, how starlight and black hole radiation heat and stir that gas, how turbulence and magnetic fields shuffle energy around. Nothing here is a detonation that makes a hole by magic. It is all the usual story of gravity plus cooling repeated patiently. The thresholds are simple guides. Cores heavier than a few times the Sun tend to become black holes. Very heavy stars may skip the neutron star step altogether. On the small end, there are speculative ideas about primordial black holes, tiny holes formed in the early universe from unusually dense ripples, but those remain unconfirmed. The reassuring theme is that black holes form when pressure loses the contest to gravity in a compact region. The rest is bookkeeping. How much mass was there to begin with? How much fell back after any explosion? How much more arrives later from the galaxy's slow rivers of gas and dust? And how often neighbors fall in? Seen this way, a black hole is not a special object added to the universe. It is an allowed outcome of gravity's everyday habit of gathering things and keeping them. A black hole without food is almost invisible. Give it gas, and it becomes a gentle engine. The gas that drifts inward seldom falls straight in. It has some angular momentum, so it circles, forming an accretion disk. In the disk, neighboring rings of gas rub against each other. Friction and magnetic turbulence convert some of the orbital energy into heat. The gas radiates that heat, cools, and spirals inward. This slow inward drift is how mass moves from galaxy scales down to the horizon. There is a practical ceiling to how bright accretion can be. Shine too strongly, and the radiation pushes back on the infalling gas. That balance is called the Eddington limit. Many black holes feed below that limit for long stretches, glowing steadily. Some flare above it briefly, pushing away some of their meal with winds. Over millions of years, such feeding can grow a seed black hole into a giant. The growth rate depends on how often gas reaches the center and how often feeding is interrupted by the black hole's own feedback, winds and jets that heat the very gas they need to eat. Feedback sounds circular, but it builds a quiet rhythm at the galaxy scale. Feed, warm the surroundings, star formation slows, the supply thins, the black hole dims, gas cools again, and the cycle resumes. In some galaxies, especially early in cosmic time, the disk near the hole glows so brightly that we see a quasar, a beacon that can outshine the galaxy that hosts it. The bright part is not the hole, it's the hot, thin gas very close to the horizon. A small fraction of feeding black holes also launch jets, narrow relativistic streams of plasma guided by magnetic fields tied to the spinning disk or the spinning hole. These jets can travel far into intergalactic space, depositing energy into surrounding gas and shaping future star formation. Even low-key feeders can stir their neighborhoods. Gentle outflows push on gas, sound waves ripple through galaxy clusters, and the pace at which new stars form rises or falls in response. On the small scale, in X-ray binaries, where a stellar mass black hole draws gas from a companion star, we see the same story compressed. Disks grow hot and switch states. Jets flicker on and off. Light curves wander in patterns that repeat across objects of vastly different masses. None of this requires explosions or drama at the horizon. Gravity and magnetism do the work. Matter heats and cools. Pressure pushes and yields. The black hole itself keeps the simplest role. It curves space-time and accepts what crosses the line. Its doing is passive but consequential. By taking in mass and angular momentum, the hole slowly changes its size and spin, and by allowing disks and jets to form just outside, it turns a quiet gravitational well into a softly regulating part of a galaxy's long life. It helps to name the landmarks in the calm geometry around a black hole. The event horizon is the point of no return, not a surface you could bump. It's where outward-aimed light no longer increases its distance from the center. Just outside that is the photon sphere, a special radius where light can orbit in unstable circles. A little farther out for matter is the innermost stable circular orbit, ISCO. Inside the ISCO, there are no steady circular orbits. Gas plunges inward quickly. The exact sizes of these radii depend on spin. In a non-spinning, Schwarzschild black hole, the horizon sits at 1 Schwarzschild radius, the photon sphere at 1.5, and the ISCO at 3. For a spinning Kerr hole, everything shifts inward along the spin's direction. The ISCO can be much closer for prograde orbits and farther for retrograde ones. Spin also introduces the ergosphere, a region outside the horizon where space itself is dragged around so strongly that nothing can remain at rest with respect to distant stars. In the ergosphere, it's possible for processes to extract rotational energy from the hole, one ingredient theorists use to explain powerful jets. For observers, these landmarks show up as gentle signatures. Gas orbiting near the ISCO emits light that is Doppler boosted on the approaching side and redshifted on the receding side, broadening spectral lines into asymmetric shapes that X-ray telescopes can measure. The tangled magnetic fields above the disk polarize the light. Polarization angles trace the geometry near the hole. Very close to the horizon, strong gravity bends paths so much that a distant camera sees a shadow, a dark interior against a brighter ring. Not because the hole glows, but because light rays that would have come to the camera instead fall in. The Event Horizon Telescope has imaged that shadow for 2 nearby supermassive black holes, a fuzzy donut whose size and shape are consistent with the simple predictions of general relativity. These measurements do not show the interior. They map the space just outside, the quiet curves of geometry. All of this can be understood without imagining violent edges. Space near a black hole is like a slowly tightening spiral staircase. Steps are normal where you walk, but the staircase curves in such a way that all paths eventually descend. Light takes paths you can chart, matter follows curves you can compute, and the familiar notions of closer and farther keep their meaning until the horizon itself, where the arrows on your map relabel into new ones that all point inward. In that spirit, the anatomy is just a set of radii where particular behaviors change, not a set of traps or gadgets. Photons swirl a little, matter orbits until it cannot. Magnetic fields tap rotation where they can, and the whole, indifferent, supplies the geometry that makes these quiet thresholds exist. If you hovered safely far from a black hole with a very accurate clock and watched a probe fall, you would notice something unhurried. As the probe approaches the horizon, the light it sends you arrives more and more redshifted and delayed. The probe's onboard clock ticks normally for the probe, but for you, its ticks get farther apart. Its last signals pile up and fade. From your vantage, the probe seems to slow and dim, never quite crossing the horizon in any finite time you read. That is an optical story, not a physical barrier. The probe's own experience is straightforward. It crosses the horizon in a finite proper time with no bang, no flash, only a gradual change in what directions are available to travel. In a supermassive black hole, tidal forces at the horizon can be tiny. The difference in gravity between head and feet could be smaller than what you feel standing up on Earth. Only well inside does the tidal stretching become severe, the spaghettification often described, but even that is a predictable gradient, not an explosion. Signals sent outward after the crossing cannot get back to you. Signals sent inward reach the center in a finite time, and then, according to the classical equations, hit the singularity where the description ends. Along the way, light behaves politely. Rays that skim close to the black hole bend. Some loop around once or twice before escaping. Some never return. The sky as seen by the falling probe distorts. Stars behind appear to smear into a bright ring. The black region ahead swells. If the black hole is spinning, frame dragging makes space itself swirl. The direction of straight ahead twists slowly, and gyroscopes precess even while feeling no force. None of this breaks intuition, it only relabels it. Energy and momentum are conserved along paths. The redshift is just bookkeeping for how hard light must climb out of the potential well. Time dilation is just the gravity-altered geometry telling clocks to pace themselves differently at different heights. On the outside, this slowness makes black holes seem like patient absorbers. Infalling matter may take many orbits near the ISCO, shedding energy gently, lighting up the disk. On the inside, once past the horizon, there is no chance to stop or turn around. Every route forward shortens the remaining time to the center. For a stellar mass black hole, that time can be milliseconds. For a supermassive one, minutes to hours. In either case, it is uneventful in the sense that nothing locally announces a special surface has been crossed. The drama is in the geometry, not in fireworks. If your goal is sleep, it helps to imagine that the universe keeps orderly accounts even here. Light shifts color to pay its bill. Clocks keep different schedules depending on altitude. Trajectories curve with a grace that is hard to see in a flat diagram, but simple once you let space be curved. Ask what lies inside a black hole, and the classical answer is short. A singularity, a place where paths end and space-time curvature becomes unbounded. But place here is slippery. In the simplest, non-spinning black hole, the singularity is not a point you could stand next to. It's a space-like surface in your future, more like tomorrow than like a dot in a room. You cannot go around it or wait it out. Once you cross the horizon, all routes forward reach it in finite proper time. In a spinning black hole, the analytic solutions contain richer structures, inner horizons, rings, even mathematically allowed passages. But realistic physics suggests these features are unstable. Tiny disturbances grow, and the tidy interior becomes a turbulent end state rather than a neat corridor. This is wrapped in a conjecture called cosmic censorship. Nature hides the worst pathologies behind horizons, keeping the outside world sane. Whether censorship always holds is an open question under active study, but observationally, we see horizons behaving as expected, with no naked singularities on display. The honest part is that quantum gravity, our not yet finished theory that marries quantum rules to curved space-time, must take over before the classical singularity is reached. Quantum effects could smear or replace the singularity with something finite. A bounce, a phase transition, a new kind of core. We do not have data from inside, and we may never because the horizon blocks outbound messages. Information theory puzzles sharpen the issue from the outside. If black holes evaporate extremely slowly by Hawking radiation, as theory predicts, what happens to the information about the things that fell in? Does it come out encoded in subtle correlations in the radiation, preserving unitarity, the quantum rule that information is never lost? Or is information genuinely destroyed? Most physicists now expect unitarity to be preserved, with the horizon and its near-surface quantum degrees of freedom playing a role. Proposals include soft hair that records details, or a more holographic accounting where the interior is encoded on the boundary. Dramatic ideas like firewalls, energetic surfaces replacing the calm horizon, were raised to force clarity. The consensus is not settled, but each step pushes us to formulate what we mean by inside more carefully. From a sleepy vantage, the safe answer is modest. Classically, the interior is a smooth fall to an end of predictability. Quantum mechanically, we expect new rules before the end, but we do not yet know their exact script. None of this changes the outside behavior we can measure. Horizons cast the expected shadows. Accretion disks heat and cool as predicted. Mergers ring down with waves that match the simple geometry we trust. The interior is where curiosity touches the edge of current knowledge. It is not chaos let loose. It is a quiet notice that the map ends and the next page is under construction. If black holes don't emit light, how do we know they're there? We look for the most ordinary things: how other things move, how gas heats as it falls, and how light is bent along the way. In our own galaxy, some black holes live in X-ray binaries, a black hole with a normal star companion. The black hole's gravity quietly siphons gas from the star. That gas circles in an accretion disk, rubs against itself, heats to millions of degrees, and shines in X-rays before slipping inward. The star itself wobbles in a regular orbit. By measuring the wobble speed and period, astronomers infer an unseen compact mass too heavy to be a neutron star, pointing to a stellar mass black hole. On larger scales, entire galactic centers tell the tale. Stars near the middle of the Milky Way, called the S-stars, race on tight ellipses around an invisible focus. Their speeds and paths say a mass of about 4 million suns sits inside a region smaller than our solar system, too dense to be anything but a supermassive black hole. Gas near other galaxies' centers broadens spectral lines by moving incredibly fast, and its time delays when it brightens and dims, reverberation mapping. Let us estimate how far the gas sits from the center, and hence how massive the central object must be. We also watch for gravitational lensing, where mass bends light. A black hole or a dense cluster can act like a lens, magnifying or warping the images of background galaxies. Sometimes we can even see a single star's brightness spike as a compact object passes in front, microlensing, hinting at populations of dark compact masses. Black holes also leave timing fingerprints. In X-ray binaries, their disks flicker with quasi-periodic oscillations, QPOs, gentle rhythms linked to orbits near the innermost stable path. In active galactic nuclei, slow, red noise variability, brightening and fading over days to years, reveals the shuffling of gas in a deep potential well. On the high-energy end, when jets are pointed near our line of sight, a blazar, light arrives in bursts that are fast and structured, showing that compact engines are at work with magnetic fields tapping rotational energy. None of these observations needs us to see inside the hole. They are all outside stories: motion of stars, glow of hot gas, bending of light, echoes in time. Put together, they paint a consistent picture that works across mass scales: tens of suns in binaries, millions to billions of suns in galaxy centers. The same basic geometry, an event horizon shaping space just outside, explains the size of the black hole shadow imaged in radio, the broadened iron lines in X-rays, and the precise chirps in gravitational waves when two black holes merge. The power of the evidence isn't in a single smoking gun, it's in the agreement of many quiet clues, each one pointing to compact, dark, heavy objects that curve space-time exactly as general relativity predicts. Imaging the immediate neighborhood of a black hole means seeing detail as fine as reading a newspaper in New York from Europe. No single telescope can do that, so astronomers linked radio dishes across Earth into a virtual planet-sized telescope called the Event Horizon Telescope, EHT. By recording radio waves at multiple stations and combining them with a technique called very long baseline interferometry, the EHT reconstructs an image of structures the size of a few black hole radii in nearby giants. The first big target was M87 star, the supermassive black hole in the center of the galaxy M87. The EHT image showed a bright ring surrounding a dark interior, the shadow. The ring is bright where the hot plasma in the accretion flow beams radio emission toward us and where light paths are focused by gravity. The dark center is not the hole glowing, but the region where light rays that could have reached us are instead captured. The measured ring size matches the photon orbit scale predicted by general relativity for a black hole of M87's known mass and distance, and the overall shape is consistent with a Kerr-spinning black hole rather than any wild alternative. Later, the EHT imaged Sagittarius A star at our own galaxy's center. Because Sagittarius A star is much smaller, gas whips around it on timescales of minutes, so the image is blurrier, like photographing a candle flame in a breeze. But again, the effective ring size and brightness pattern match expectations for a compact horizon. Beyond pictures, the EHT measures polarization, the orientation of radio waves, which traces magnetic fields near the hole. Polarization maps around M87 star show organized fields that can help launch and collimate the enormous jets streaming from that galaxy's core, consistent with theories where magnetic fields tap the hole's spin energy. Importantly, EHT results aren't used in isolation. They sit alongside stellar orbits, X-ray spectra, and jet kinematics. Each adds a layer. The EHT's ring size constrains any idea that tries to replace black holes with exotic objects. A boson star or gravastar must mimic the same lensing and shadow to survive, and many simple versions don't. The images also test gravity itself. Any departure from general relativity strong enough to warp the photon orbit significantly would show up as a wrong-sized or wrong-shaped ring. So far, within uncertainties, Einstein's geometry passes. The biggest lesson is humble. Close to the horizon, nature looks simple. The brightness varies with time, turbulence stirs, but the gross geometry, ring scale, shadow depth, polarization swirl, behaves like a calm metric written a century ago. For a sleepy mind, that's comforting. We don't need fireworks or exotic mechanisms to draw a donut. We need a hot, magnetized flow outside a quiet boundary where outward no longer exists, and a patient array of dishes to listen in unison to the radio, whisper of curved space. When two black holes orbit each other, they gradually lose energy by radiating gravitational waves, tiny ripples in space-time that stretch and squeeze distances as they pass. As energy is lost, the holes spiral closer and move faster. The emitted waves rise in frequency and amplitude, tracing a chirp. Ground-based detectors like LIGO and Virgo use kilometer-scale laser interferometers to sense changes in arm length smaller than a proton's width as a wave passes. The signals are faint but distinctive. The inspiral phase is a clean, predictable dance where general relativity lets us compute the waveform. It reveals the binary's masses and spins. The merger is a brief, loud crash where two horizons merge into one. The ringdown is the final decaying tone as the new black hole settles, radiating its deformed shape away in a set of characteristic frequencies called quasi-normal modes, the notes of the black hole. Since 2015, dozens of black hole mergers have been heard. They tell us that stellar mass black holes come in a wider mass range than we once expected, sometimes 30 suns or more, sometimes in unusual pairings, sometimes with spins aligned, sometimes not. Hints about how they formed, in isolated binaries or in crowded clusters. The signals also test gravity. The speed of gravitational waves matches the speed of light to high precision. The inspiral merger ringdown sequence fits general relativity's templates. Any large deviations would have stood out. By measuring the ringdown's tone and decay, we check whether the final object's mass and spin are consistent with the earlier inspiral's accounting. An internal consistency check of the theory's no-hair expectation that black holes are fully described by mass and spin, not extra multipoles. So far, the checks are calm and boring in the best way. Everything adds up. In a sleepy video, it's nice to think of these events not as cosmic crashes, but as long, slow tides in space-time that only get busy in the last blink of the dance. Future detectors will broaden the band. LISA, a planned space interferometer, will hear supermassive black hole mergers and extreme mass ratio inspirals where a small compact object orbits a giant for years, tracing space-time's geometry with exquisite precision like a bead sliding along a twisted bowl. Pulsar timing arrays listen at nanohertz for a background hum from many supermassive binaries at once. Together, these instruments turn black holes from silent silhouettes into audible instruments whose notes encode mass, spin, distance, and even cosmic history. The quiet triumph is that waves from entirely different sources, colliding black holes, confirm the same geometry that images and spectra see. The universe hums the same tune that it draws. Black holes don't just eat, they also organize their neighborhoods through outflows, winds, and jets. Close to the horizon, magnetic fields anchored in the swirling plasma can be wound up by rotation. In some theories, those fields tap the rotational energy of the spinning hole itself, the Blandford-Znajek process, launching narrow relativistic jets along the rotation axis. In others, they fling material from the inner disk like a cosmic slingshot, the Blandford-Payne process. Whatever the exact mix, the consequence is a pair of narrow beams that carry energy and momentum far beyond the galaxy's core. At galactic cluster scales, jets inflate bubbles in the hot, X-ray bright gas that fills the spaces between galaxies. The bubbles rise like balloons and deposit heat through gentle sound waves and turbulence. This maintenance mode feedback prevents the gas from cooling too quickly and forming too many new stars, helping explain why the largest galaxies aren't absurdly blue and overgrown. On smaller scales, when accretion is bright and near the Eddington limit, winds from the disk can sweep through the inner galaxy, clearing gas and dust and briefly quenching star formation. Over millions of years, black hole feeding and feedback fall into a duty cycle. The hole grows, shines, warms, and stirs the gas, then dims. The gas cools, drifts inward again, and the cycle repeats. Observations back this quiet choreography. Radio maps show lobes and cavities carved by jets. X-ray images reveal ripples and edges where bubble rims press on hot gas. Optical spectra catch outflowing gas at hundreds to thousands of kilometers per second. Infrared observations see dust pushed and heated. Even in low-power states, jets in small systems, like X-ray binaries, scale in a way that mirrors supermassive systems, a fundamental plane linking radio power, X-ray power, and black hole mass. This scaling suggests that the same engine, the same magnetized disk near a horizon, operates across 8 orders of magnitude in mass. It's tempting to picture jets as violent lances, but their global effect is often smooth, adding just enough heat and turbulence to keep the gas honest. In the long view, black holes act like thermostats for their galaxies and clusters, not by intent, but by feedback physics. Accrete too fast, and you heat the pantry. Heat the pantry and the food supply thins. Thin the supply, and you quiet down. The result is galaxies that age with some restraint, clusters whose central gas avoids catastrophic cooling, and a universe where the brightest engines prevent their own excess with the most ordinary tool, back reaction, playing out over quiet cosmic decades. Long before we could image shadows or hear chirps, theorists noticed a deep analogy. Black holes obey laws that echo thermodynamics. The area of a black hole's event horizon never decreases in classical processes, Hawking's area theorem. Much like entropy, a measure of disorder never decreases for isolated systems. The surface gravity at the horizon behaves like a temperature in the equations, and the mass acts like energy. Jacob Bekenstein took the analogy seriously and proposed that a black hole's entropy is proportional to its horizon area, not its volume, a startling idea tying information content to a surface. Then Stephen Hawking added a quantum twist. When you include quantum fields near the horizon, black holes are not perfectly black. They radiate with a thermal spectrum at a temperature inversely proportional to their mass. For a stellar or supermassive black hole, this Hawking radiation is unimaginably faint, far overwhelmed by the glow of any surrounding gas. But in principle, it means black holes have a temperature, an entropy, and over fantastically long times, they evaporate. For a solar mass black hole, the temperature is a tiny fraction of a Kelvin, and the evaporation time is approximately 10 to the 67th power years, longer than the current age of the universe by many orders of magnitude. The formulas sharpen a grand theme. Gravity, quantum mechanics, and information are entangled. The entropy-area relation suggests that the number of microstates, a count of hidden configurations, scales with surface area, hinting at a holographic principle where physics inside a region can be encoded on its boundary. In certain high-energy theories, string theory, one can even count microstates for special black holes and reproduce the Bekenstein-Hawking entropy, giving weight to the idea that this thermodynamics is not just metaphor. In the lab, we can't see Hawking radiation from astrophysical holes, but we can build analog horizons in fluids, optical fibers, and Bose-Einstein condensates where waves see an effective point of no return. Some experiments report thermal spectra consistent with Hawking-like emission. These analogues don't prove the cosmic case, but they support the mechanism. Horizons and quantum fields naturally produce pair creation and asymmetric escape that looks thermal to distant observers. The thermodynamic laws of black holes also guide astrophysics. The no-hair idea, mass and spin suffice, matches how ringdowns behave. The generalized second law, which says black hole area plus ordinary entropy never decreases, constrains wild thought experiments about what you can toss into a hole. And Hawking radiation fuels the information paradox. If evaporation is exactly thermal, where does the detailed information about the infallen stuff go? Modern work suggests subtle correlations in the radiation, reflected in a page curve that rises and then falls, can preserve unitarity, but the precise bookkeeping is active research. For our sleepy tour, the moral is gentle. Even the darkest objects have a temperature. Even the most absolute horizons participate in the ordinary bookkeeping of energy, entropy, and information. And the calm area of a shadowed boundary tells you something exact about the number of hidden states that could have made it. General relativity does not just predict horizons, it predicts small, precise departures from Newton's gravity. Near a black hole, bound orbits don't close neatly. They precess, meaning the point of closest approach shifts each lap. Light climbing out from deep near the hole redshifts, losing energy and sliding to longer wavelengths. Gyroscopes precess in the gentle twist of space-time. Time itself ticks a little slower, lower down. The stars around Sagittarius. A star provides a sleepy laboratory for these effects. Over decades, astronomers have traced the paths of fast S-stars, especially the star S2, which swings within light hours of the black hole every 16 years. During pericenter passage, S2's light showed the gravitational redshift expected at that depth. After a full orbit, the Schwarzschild precession, a small forward rotation of the ellipse, matched Einstein's prediction. No fancy additions were needed. The numbers line up with a 4 million solar mass compact object at the center. Closer still, we look at gas rather than stars. In bright accreting systems, iron atoms in the disk fluoresce at a characteristic X-ray energy. Near the hole, Doppler shifts and gravitational redshift broaden and skew this line into a lopsided hump whose shape records the inner disk radius and thus the black hole spin. As flashes travel around the inner disk, echoes arrive after tiny delays. By mapping these reverberation lags, we sketch the disk's vertical structure. Sometimes the X-ray light curves show quasi-periodic oscillations, hints of hotspots or disk oscillations near the innermost stable orbit, tapping directly into the orbital timescales of curved space. Even radio hotspots near Skr A star, seen by the EHT as brief flares that seem to loop, suggest compact blobs orbiting very close in, again at periods set by the deep potential well. Each of these measurements is small and patient. An extra redshift of a few parts in 1,000, a precession of a few degrees per orbit, a line broadened just so. But together they turn an abstract metric into metered geometry. If gravity were different at these scales, if extra forces pushed, or if horizons were replaced by reflective walls, we would expect echoes in gravitational waves after mergers, odd lobes in the EHT images, or wrong precession rates in stellar orbits. So far, the sky is boring in the best way. It delivers the same quiet corrections every time. For a sleep-bound listener, there's comfort in that repetition. The universe behaves like a well-tuned clock near its deepest wells. The hands precess a little. The chimes ring slightly late. But the pattern repeats night after night, orbit after orbit, in ways we can predict, measure, and trust. When people hear spaghettification, they picture a violent snap, as if a star hits a wall. The real process is quieter and more predictable. Gravity's strength changes with distance, so one side of an object feels a slightly stronger pull than the other. That difference is a tidal force. Near Earth, tides tug the oceans. Near a black hole, the gradient can be so steep that it stretches a star along the line to the hole while squeezing it sideways. There's a simple yardstick called the tidal radius. If a star passes within this distance, the black hole's tidal pull across the star exceeds the star's own self-gravity and the star comes apart. For a supermassive black hole and a sun-like star, this radius can be far outside the event horizon, which means the disruption happens where light can still escape, letting us watch. The star is not shattered like glass. It is unbound over hours to days, with about half its gas flung outward onto long, thin orbits and the other half captured into highly eccentric streams that swing back and begin to circularize through gentle collisions and shocks. As the debris settles into a nascent accretion flow, it heats and glows in ultraviolet and X-rays. Telescopes see a slow rise and a months-long fade that often follows a T to the power of negative 5/3 decline, a signature of how the most bound debris returns first and the rest trickles in. These events are called tidal disruption events, TDES, and they have become a practical way to weigh dormant black holes in quiet galaxies, because a flare at a galaxy's center with those timescales and colors is a good clue that a black hole just shredded an unlucky star. The drama is in the geometry, not in explosions. The long stream of gas can precess as it passes close to the hole. General relativity slightly rotates the orbital plane, and where streams collide, they dissipate orbital energy into heat, helping a disk form. The light can be partly hidden by dust in the nucleus, reprocessed into infrared. Sometimes winds carry away a fraction of the inflow, shaping the light curve. If the black hole spins and the returning flow aligns just so, magnetic fields can tap energy and launch a jet, and we see a different flavor of TDE with bright radio emission. For smaller, stellar mass black holes eating stars is rare because stars are larger than the tight orbits where those holes live. In contrast, supermassive holes at galactic centers sit where wandering stars or loosely bound binaries occasionally wander too close. So TDES are a slow, steady trickle over cosmic time, perhaps once every 10,000 to 100,000 years per galaxy. But with billions of galaxies, enough to keep our surveys busy. Spaghettification itself is just the end of a tidy calculation. The tidal gradient overwhelms cohesion. Matter follows geodesics that converge inward and diverge outward. The result is a ribbon, then a stream, then a glowing spiral. The star's fate reads like a set of instructions written in gravity's patient handwriting. Approach, stretch, unwind, return, collide, settle, and fade. Even the most colourful name turns out to describe an orderly process that helps us take a quiet census of hidden giants. Not all black holes are alike. They differ mainly by mass, and mass sets their neighbourhoods and habits. At the small end are stellar mass black holes, roughly a few to a few dozen times the mass of the Sun, born from the collapse of massive stars or from mergers of smaller compact objects. We find them in X-ray binaries, siphoning gas from a companion star, where the disk heats to millions of degrees and flickers with patterns that reflect the innermost orbits. We also hear them when two of them merge in a gravitational wave chirp. Their horizons are small, kilometers across, so their clocks run fast. Orbits near the ISCO take milliseconds. Flares can rise and fall in heartbeats. At the largest end are supermassive black holes, weighing millions to billions of suns, anchoring the centers of galaxies. Their horizons are as large as planetary orbits. The innermost orbits take minutes to hours. Their disks shine across the spectrum if fed. Their jets can carve radio lobes bigger than galaxies. Their gravity sculpts the motion of central stars, which let us weigh them cleanly, as with the S stars near Sagittarius A star. Between these two bookends lies a long-suspected, harder-to-spot class. Intermediate mass black holes, IMBHs, with hundreds to hundreds of thousands of solar masses. IMBHS would bridge formation pathways, perhaps born from runaway collisions in dense star clusters, from direct collapse of unusually massive early stars, or as remnants of direct collapse gas clouds at high redshift. Evidence is mounting but cautious. Some ultraluminous X-ray sources in nearby galaxies are brighter than a stellar mass black hole should be if feeding at the Eddington limit. A fraction of these may be IMBH candidates. Others are stellar holes briefly exceeding the limit. A few dwarf galaxies show nuclear masses too large for star clusters and too small for classic supermassive holes, hinting at intermediate seeds. Gravitational waves have also found mergers in the upper stellar mass range, producing remnants of around 100 suns, nudging into IMBH territory. Why does the zoo matter? Because it tells a growth story. To explain billion solar mass black holes powering quasars less than 1 billion years after the Big Bang, we either need rapid feeding or large seeds, perhaps IMBHS, formed directly from early gas. Dwarf galaxies and globular clusters are natural hunting grounds. A central IMBH would subtly broaden stellar motions or cause occasional tidal disruptions of small stars. Sensitive radio and X-ray observations can set limits or find faint accretion glows. Across the zoo, mass also shapes tidal stories. A sun-like star can be torn apart outside the horizon by a black hole up to about 100 million solar masses. Above that, the star would cross the horizon intact, swallowed whole, hiding the fireworks. Spin plays across all masses, shifting the ISCO inward for prograde orbits and outward for retrograde ones, altering how brightly a given mass can glow when fed. Yet despite this range, the same simple geometry ties them together. Rings of hot gas, photon orbit shadows, jets when the magnetic configuration cooperates, and gravity's slow habit of turning orbits into heat and light. Small holes whisper quickly, big ones hum slowly, intermediates would sing in between. The zoo is not a menagerie of different species, so much as a single animal at many sizes, with the same bones scaled up and down. Quasars, brilliant beacons seen when the universe was less than 1 billion years old, host black holes weighing hundreds of millions to billions of suns. Growing that large so fast is a steady bookkeeping problem. How much fuel, how efficiently is it converted to light, and how constantly can the engine run? If accretion proceeds at the Eddington limit, where radiation pressure balances gravity, a black hole's mass grows exponentially with an E-folding, salpeter, time of about 45 million years for a typical radiative efficiency. From a stellar mass seed of 10 suns, you would need many E-folds to reach 1 billion, which is tight but not impossible if feeding is near continuous. The catch is that real galaxies are messy. Gas has angular momentum to shed. Supernovae stir the supply. Feedback from the growing hole itself heats and blows on the pantry. Two broad solutions help. One is to start with bigger seeds. In metal-poor early halos, where gas can't cool efficiently and fragment into many small stars, a massive direct collapse of a gas cloud might form a black hole of 10 to the power of 4 to 10 to the power of 5 solar masses in one step, skipping the small seed bottleneck. Such seeds would live in small protogalaxies and later merge into bigger systems, carrying their mass upward. The second is to allow episodes of super Eddington feeding, short periods where dense, optically thick flows deliver mass faster than the nominal limit, with much of the radiation trapped and advected inward rather than pushing the gas away. Simulations suggest these phases can occur in gas-rich early galaxies, especially after mergers that funnel material to the center. Neither path requires miracles. Each is an incremental change in initial conditions or flow geometry. Observations prod the story. The tight correlation between present-day galaxy bulge mass and central black hole mass hints at co-evolution through feedback. Feed the hole, heat the bulge gas, regulate star formation, and further feeding. Dwarf galaxies with undermassive or overmassive holes relative to their bulges offer clues about early seeding and later growth. Some dwarfs seem to host surprisingly hefty black holes, which favors large seeds. Others are quiet, suggesting many seeds stalled. The cosmic X-ray background, aglow from countless faint accretors, constrains how much gas black holes as a population have eaten over time. High redshift quasars show metal-poor environments and rapid dust formation, consistent with intense early star formation that both feeds and obscures the growth. On the limiting side, angular momentum is the stubborn gatekeeper. Gas must shed it via gravitational torques, bars, spiral waves, or cloud-cloud collisions. Too much feedback, and the gas is pushed out. Too little, and the nucleus chokes on its own crowding and star formation beats accretion to the fuel. The result is a growth curve that is neither smooth nor rare. It is bursty, with long lulls and brief binges. By the time the universe reaches middle age, many galaxies host quiescent giants that barely feed. Only a fraction are active at any given time. The giants' very existence, lit as quasars when the universe was young, tells us the early cosmic kitchen was well stocked in some neighborhoods, and that the rules for shedding angular momentum and surviving feedback were met often enough for a few engines to grow huge in a hurry. No single trick explains it. It is accumulation of small, ordinary steps, steady inflow, occasional overfeeding, and mergers where holes combine and skip a rung on the ladder. When two black holes orbit, the dance lasts for ages, but the last few orbits and the merger itself happen quickly. In those final moments, the system radiates a burst of gravitational waves that carry away not just energy, but also linear momentum and angular momentum. Because the waves aren't emitted perfectly symmetrically, spin orientations and mass ratios matter. The merged black hole can receive a recoil, a kick that pushes it relative to the surrounding stars and gas. The physics is exacting, but not violent in the cinematic sense. It is conservation laws keeping score. Numerical relativity simulations that solve Einstein's equations on supercomputers predict kicks from tens to thousands of kilometers per second. In most galaxies, even a few hundred kilometers per second can displace the remnant from the center for a while. In tiny dwarf galaxies, the remnant could be ejected, leaving a nucleus briefly empty and seeding black holes to wander. Astronomers hunt for such recoiling black holes by looking for off-center active nuclei or for quasars with broad emission lines shifted relative to their host galaxies. A few candidates exist, though alternate explanations, like binary motion, often compete. The merger's aftermath is the ring-down, when the deformed horizon settles by radiating a set of discrete tones, the black hole's quasi-normal modes, whose frequencies and decay times depend only on the final mass and spin. Detecting multiple modes would let us perform black hole spectroscopy, checking whether the spectrum matches Kerr predictions. Early detections already confirm the broad picture, and future, louder events may let us pick out additional notes. Mergers also stir the accretion story. In a gas-rich galaxy, two supermassive black holes brought together by a galaxy merger will orbit for millions of years, interacting with stars and gas, forming a binary at parsec scales. Gas can form a circumbinary disk with streams feeding mini-disks around each hole. Periodic brightening may betray their presence. As gravitational radiation takes over at small separations, the holes plunge together. If a kick follows, the remnant may carry its mini-disk like a collar, producing a transient flare as it oscillates through the galactic core. At larger scales, repeated mergers build black hole spin histories. Frequent random mergers tend to average spins down. Long coherent accretion along one plane tends to spin holes up. Spins matter for jet power and for the brightness of accretion, since a higher spin pulls the ISCO inward, letting more gravitational energy become light. For stellar mass holes in clusters, three-body encounters can harden binaries and swap partners, leading to mergers with spins and mass ratios that differ from those formed in isolated stellar binaries. Gravitational waves already hint at both formation channels. In every case, the narrative is not drama, but accounting in curves. Orbits decay as waves carry angular momentum away. Two horizons touch and become one. The new horizon rings like a struck bell. Sometimes the bell slides a little in its mount and later drifts back. Over billions of years, these quiet sums, tiny asymmetries integrated across countless inspirals, help sculpt where black holes live, how fast they spin, and how their galaxies remember the last close dance their nuclei performed. When two black holes orbit, the dance lasts for ages, but the last few orbits and the merger itself happen quickly. In those final moments, the system radiates a burst of gravitational waves that carry away not just energy, but also linear momentum and angular momentum. Because the waves aren't emitted perfectly symmetrically, spin orientations and mass ratios matter. The merged black hole can receive a recoil, a kick, that pushes it relative to the surrounding stars and gas. The physics is exacting but not violent in the cinematic sense. It is conservation laws keeping score. Numerical relativity simulations that solve Einstein's equations on supercomputers predict kicks from tens to thousands of kilometers per second. In most galaxies, even a few hundred kilometers per second can displace the remnant from the center for a while. In tiny dwarf galaxies, the remnant could be ejected, leaving a nucleus briefly empty and seeding black holes to wander. Astronomers hunt for such recoiling black holes by looking for off-center active nuclei or for quasars with broad emission lines shifted relative to their host galaxies. A few candidates exist, though alternate explanations, like binary motion, often compete. The merger's aftermath is the ring down, when the deformed horizon settles by radiating a set of discrete tones, the black hole's quasi-normal modes, whose frequencies and decay times depend only on the final mass and spin. Detecting multiple modes would let us perform black hole spectroscopy, checking whether the spectrum matches Kerr predictions. Early detections already confirm the broad picture, and future louder events may let us pick out additional notes. Mergers also stir the accretion story. In a gas-rich galaxy, two supermassive black holes brought together by a galaxy merger will orbit for millions of years, interacting with stars and gas, forming a binary at parsec scales. Gas can form a circumbinary disk with streams feeding mini-disks around each hole. Periodic brightening may betray their presence. As gravitational radiation takes over at small separations, the holes plunge together. If a kick follows, the remnant may carry its mini-disk like a collar, producing a transient flare as it oscillates through the galactic core. At larger scales, repeated mergers build black hole spin histories. Frequent random mergers tend to average spins down. Long coherent accretion along one plane tends to spin holes up. Spins matter for jet power and for the brightness of accretion, since a higher spin pulls the ISCO inward, letting more gravitational energy become light. For stellar mass holes in clusters, three-body encounters can harden binaries and swap partners, leading to mergers with spins and mass ratios that differ from those formed in isolated stellar binaries. Gravitational waves already hint at both formation channels. In every case, the narrative is not drama, but accounting in curves. Orbits decay as waves carry angular momentum away. Two horizons touch and become one. The new horizon rings like a struck bell. Sometimes the bell slides a little in its mount and later drifts back. Over billions of years, these quiet sums, tiny asymmetries integrated across countless inspirals, help sculpt where black holes live, how fast they spin, and how their galaxies remember the last close dance their nuclei performed. Because horizons hide interiors, it's natural to ask whether some exotic alternatives could mimic a black hole from the outside. Could there be ultra-compact stars made of unusual matter, or objects with surfaces that sit just outside the would-be horizon, or wormholes that look like holes from far away but open elsewhere? Candidates have names: boson stars, made of coherent fields rather than ordinary particles; gravastars, gravitational vacuum condensates with thin shells; fermion balls, dense configurations of dark matter; or wormholes stabilized by exotic ingredients. Each promises to be very compact and dark, but each also faces quiet tests that our telescopes already perform. First, shadow size and shape. The Event Horizon Telescope measures the effective photon orbit and the dark interior against a bright ring. Any alternative must lens light almost exactly like a Kerr black hole of the measured mass. Many simple constructions fail that precision or require fine-tuned parameters to pass. Second, ring-down tones. When two compact objects merge, the final object rings with quasi-normal modes. Kerr black holes have a very specific spectrum determined solely by mass and spin. If the object has a reflective surface instead of a horizon, you could get late-time echoes in the gravitational wave signal as waves bounce inside. Careful searches have not found robust, repeatable echoes, and the observed ringdowns agree well with Kerr. Third, surface emissions. If there is a literal surface just outside the horizon, infalling matter should smack into it and produce a persistent heat glow distinct from the behavior of a horizon that simply accepts matter. For the supermassive object in our own galaxy and in other quiet nuclei, limits on any steady thermal surface emission are stringent. They favor a true horizon over a hard surface. Fourth, tidal disruptions and orbital precession. Stars and gas near a star follow paths whose tiny relativistic shifts match general relativity's expectations. Alternatives with different near-field geometry can slip on these detailed tests. Fifth, accretion efficiency. How bright a disk can be for a given mass inflow depends on how deep the gravitational well is and where the innermost stable orbit sits. X-ray spectra and timing in binaries and active galactic nuclei are broadly consistent with standard Kerr geometry, including the way high spin pulls the ISCO inward. None of this proves that no exotic object exists anywhere. It says that in the cases we can check, the simple Kerr description passes every gentle exam we can design, from radio images to X-ray line shapes to the tones of a post-merger bell. Wormholes remain beautiful mathematics and useful thought experiments. Boson stars are explored in simulations and may have roles in other contexts. But to masquerade as the specific compact engines we map, they must sit inside a very narrow corridor that current data keeps squeezing. The healthy posture is pragmatic. We keep testing for departures, wrong ring sizes, wrong precession, late echoes, surface glows, because every constraint improves our understanding. So far, the sky has been boring in the most satisfying way. It looks Kerr again and again across masses and messengers. Beyond being beautiful endpoints of stars and anchors of galaxies, black holes are labs where we can probe ideas that are hard to reach in any other way. One example is the hunt for ultralight bosons, hypothetical particles much lighter than anything in the standard model. Around a spinning black hole, certain boson masses would set up a resonance with the black hole's rotation through a process called superradiance. The field can extract rotational energy and grow into a big, cloudy halo, a kind of gravitational atom with the hole as the nucleus and the boson field in giant orbitals. If this happens, black holes of the matching mass range should spin down over cosmic time, avoiding very high spins. When we measure spins, from X-ray disks or gravitational wave ringdowns, and find very fast rotators in some mass windows, we can rule out boson masses that would have drained those spins. In this way, black holes quietly exclude slices of parameter space for new particles without a single particle detector underground. Another lab is the strong field regime of gravity. The innermost orbits around a black hole and the ringdown after mergers test general relativity where curvature is highest we can access. Alternative theories of gravity often introduce extra fields or couplings that would change the rate of orbital precession, the binding energy at the ISCO, or the mode spectrum of ringdowns. By comparing precise waveforms and spectral features with theory, we bound or remove these modifications. Black holes also sit inside dark matter halos. If dark matter is cold and collisionless, it can form a spike of density near the center under some formation histories. Such spikes could enhance annihilation signals for dark matter models where particles self-annihilate, producing gamma rays or other products. Lack of such signals near galactic centers modestly constrains those models or the spike's survival under mergers and feedback. If dark matter interacts weakly with black holes in other ways, e.g. forming a mini-disk, subtle timing changes in pulsar signals near a black hole or in stellar ephemerides could hint at interactions. In X-ray polarization, new missions test how light's polarization angle rotates as it skims magnetized plasma near the horizon. Deviations from expectations would ripple back into our understanding of plasma physics and the geometry. Even time delays, reverberation mapping of X-ray flares reflecting off the inner disk, serve as stopwatches for how cause and effect propagate in a curved space-time. On the gravitational wave side, the pulsar timing background now emerging opens a window onto the demographics of supermassive binaries, telling us how often galaxies carried pairs of giants to the brink. Any mismatch between expected and measured amplitudes could reflect environmental couplings, eccentric orbits, or surprises in hierarchical galaxy formation. We also use black holes to cross-check constants. Do fundamental constants drift? Spectral lines in quasar environments and precise timing in accreting systems put limits on wild drifts over cosmic time. All these are quiet tests. No fireworks, just careful comparisons of curves and tones and delays with honest equations. The appeal for a sleepy channel is that the same data that make pretty pictures and soft hums also reach into the deepest questions about what the universe is made of and what laws it obeys when gravity is at its most intense but still observable. The next decade brings a calm flotilla of instruments designed to make the black hole picture sharper without raising the volume. On Earth's surface, the Next Generation Event Horizon Telescope, NGEHT, plans more dishes, wider frequency coverage, and true movies of the inner flow, not just still frames. That will let us watch hotspots orbit, track polarization patterns as magnetic fields twist, and pin down spins and accretion geometry with fewer assumptions. Giant optical/IR telescopes, the ELT, TMT, and GMT, will resolve stars even closer to Sagittarius A star, measuring fainter objects and smaller orbits to catch higher-order relativistic effects and maybe find stellar remnants that whisper about past mergers in our core. In X-rays, missions focused on high-resolution spectroscopy and timing, like X-RISM now and Athena later, aim to measure ion line shapes, winds, and reverberation lags with new precision, mapping the vertical structure of disks and the location of the corona that shines above them. IXPE has already begun polarization studies. Future polarimeters will extend that reach. In radio, the NGVLA and SKA will map jets and lobes in detail, trace how energy travels from the innermost engine out into intergalactic space, and count tidal disruption events by their radio afterglows as jets sometimes ignite. On the time domain front, the Vera C. Rubin Observatory, LSST, will scan the sky night after night, catching flares from TDES, changing-look active nuclei that switch their disks on and off, and perhaps recoiling black holes wandering off-center in small galaxies. In space-based gravitational waves, LISA will listen to the slow dance and coalescence of supermassive black holes and the precise long serenade of extreme mass ratio inspirals, where a small compact object orbits deep in a giant space-time, mapping the metric like a bead sliding on every groove. On Earth, proposed third-generation detectors, Einstein Telescope and Cosmic Explorer, would hear stellar mass mergers across most of the observable universe, giving us sample sizes large enough to do population science, spins versus environment, mass gaps, eccentricities, tests of ring-down beyond the loudest mode. Pulsar timing arrays will add more millisecond pulsars, extend baselines, and turn the first detection of a nanohertz background into a measured spectrum, separating contributions from black hole binaries and any more exotic sources. In the microwave, improved CMB polarization maps will keep pushing for or against primordial B modes, which inform the earliest conditions that, indirectly, set the stage for how quickly black holes could grow. None of these instruments aims for a cinematic reveal. They aim for consistency, multiple independent channels telling the same quiet story about geometry, plasma, and demographics. For production, that means your sleepy video series can evolve with real news without changing tone. A new Ring movie here, a better iron line there, a gravitational wave catalogue update every observing run. Each edition is a small brushstroke on a patient portrait that already looks like a black hole, only clearer. The universe is cooperating by being predictable, which is the best compliment a theory can receive. Because the word is dramatic, everyday imagination gives black holes powers they don't have. The first myth is that black holes suck everything like cosmic vacuums. In truth, outside the horizon, gravity works just like any other mass. Replace the sun with a black hole of equal mass, ignoring the obvious effects of losing sunlight, and Earth's orbit would be unchanged. Same year, same ellipse. Things fall in only if they aim too close or lose enough angular momentum. Most matter in a galaxy keeps its distance forever. The second myth is that black holes race around eating galaxies. They sit where gravity puts them, centers of galaxies for the supermassive kind, or scattered as remnants of dead stars. Their feeding is slow, regulated by how gas can shed angular momentum. Starvation is the default. The third myth is that crossing the event horizon means getting torn apart instantly. For a supermassive black hole, tidal forces at the horizon can be mild. The stretching that earns the nickname spaghettification becomes severe inside, later, not at the edge. The fourth myth is that black holes are portals guaranteed to connect to elsewhere. Solutions to Einstein's equations allow wormholes in math. Stable, traversable versions need exotic ingredients we have no evidence for. The fifth myth treats Hawking radiation like a short fuse. Real astrophysical black holes are so cold by Hawking's formula that they will outlast stars, galaxies, and even many stages of the universe's far future. Evaporation is real but glacial. A sixth confusion is about time near a hole. From far away, things falling in seem to slow and freeze as their light redshifts. From the falling object's own clock, it crosses the horizon in finite time with no bump. Both views are correct for their observers. No paradox, just geometry. A seventh myth imagines that nothing can escape, therefore nothing can be learned. In reality, almost everything we know comes from outside regions. Hot disks glow, jets shine, stars orbit, waves ring, horizons hide interiors, not neighborhoods. An eighth assumes that the Milky Way's black hole is a hazard to Earth. It sits 26,000 light-years away. The tidal field here is negligible. The night sky is safe. A ninth confuses any dark compact mass with a black hole. Neutron stars exist and can be heavy. Careful measurements of size, surface emission, and gravitational wave tidal deformability separate the two families. Finally, some think black holes are purely destructive. In cosmic ecology, they are also constructive. Their feedback heats and stirs gas in ways that regulate star formation, keeping galaxies from burning their fuel too fast. Clearing these myths isn't scolding, it's a way to let the real, quieter story be heard. Black holes are ordinary gravity pushed to an extreme shape, operating by the same rules as everything else, merely asking you to let space curve and clocks disagree in gentle, specific ways. A black hole isn't a mouth or monster, it's a region where geometry gently removes away. The event horizon is a rule, not a wall. Cross it in a supermassive hole and nothing dramatic happens. Your clock simply flows to a future where every path ends at the classical singularity our equations can't yet describe. Outside, ordinary physics hums. Gas keeps its spin, forms an accretion disk, warms, glows, and drifts inward. Magnetic fields sometimes shape narrow jets that heat and stir galactic gas. Stray stars stretch into ribbons and settle into brief flares. Across masses, stellar, intermediate, supermassive, the same bones repeat: horizons, photon orbits, innermost stable paths, frame dragging, redshift, precession. We image rings with the Event Horizon Telescope and hear mergers chirps with LIGO. Both match Einstein's calm geometry. Thermodynamics whispers too. Area acts like entropy. Hawking temperature is tiny. Information remains an open ledger. Keep the shape, let details fade. Sleep well. Good night.